We are now familiar with a number of different circuit elements. And by that I mean things like batteries, drawn batteries like we might see them in real life, a flat part and a button on the top. And we've got resistors, which resistors are often kind of cylindrical shaped objects with a wire coming out of each end. So we've got resistors, and we've got capacitors, and our most familiar kind is our parallel plate capacitors. So it might look something like this, with the wire coming off the top and the wire coming off the bottom. And we know how to calculate all these things. The resistance of the resistor is the resistivity times the length divided by the cross-sectional area. The capacitance is based on its geometry too. Its C is equal to epsilon naught A over D. Okay, and so epsilon naught is this constant. A is the area of the plates, and D is the gap between the plates. And batteries are basically based on their chemistry. They create a potential difference between the top and bottom. This is the positive end, that's the negative end. Okay. Now in a computer or a phone or any digital device, there'll be lots of power supplies, lots of resistors, lots of capacitors, and other circuit elements, which we'll learn about later. But they're all wired together. For example, I might wire the resistor to the battery, and then I might wire the resistor to the capacitor, and then I'd hook the capacitor back to the back end of the battery. And in doing that, I create a complete circuit, because now there is a path for a flow through this circuit. The current can flow, albeit with the capacitor for a short time, but this is a complete circuit. I basically have a circle that I can go around this whole thing. And that's critical for circuits. You have to have a complete path, a returning loop coming back to it. Now, one thing that we're going to try and do is simplify it. It's kind of hard to draw it like that all the time. And so we have symbols, just like we have variables, like rho stands for resistivity, R stands for resistance. We can have symbols that represent these different circuit elements and try and simplify our efforts to draw it. So for this example, we're going to introduce batteries are going to be a circuit element that looks like this. Okay. And this symbol, will have wires still coming off of it. This symbol means that the long bar is our positive end of the battery and the short bar is the negative. Now sometimes I'll just draw one long bar and one short bar, not a double pair, because that's still sufficient to show which side's positive and negative. But often we'll get them confused with the symbol of a capacitor, and so we'll draw the double set. So long bar, short bar, long bar, short bar. And that represents the battery and tells me which side's positive. If I were to model this one here, I'd come over to a resistor, and resistors we represent with a zigzaggy line, like that. Okay. And the reason why this is chosen as the element is because that looks like the filament of a light bulb. If you look closely at an old incandescent light bulb that actually glows hot, it's got a zigzag pattern. Okay? And the goal of that is to increase the length so you can increase the resistance. And therefore it dissipates more energy by light, also by heat, but also by light. So this is our symbol for resistance, and so I'd call that a resistor. Okay, and we'll talk about which side's positive and negative in a next video. All right, and I guess I should put, this would be delta V for our source, whatever it is. I often like to put a battery there, or just a number, delta V1 or something like that, because we'll find that each of these have a voltage. Okay, now for the capacitor, to simplify things, because our most common capacitor is a parallel plate, we just do two lines parallel to each other and of equal length. So not long short like the battery, but of equal length. And then I could reconnect those wires and label that as C. So this is a circuit diagram that represents this more or less physical arrangement of objects and allows us to do it more simply in an analysis. Now, something that's important is recognizing what pieces of this diagram are important for that, or what can change and not change the physical arrangement. So, for example, this is also the same diagram right there. It's the same because if I follow the path, there is one wire connecting the positive end of the battery to the resistor with no junctions in between and nothing else in between. And then there is one wire connecting the other side of the resistor to one side of the capacitor with no junctions or any other elements in between. And then one wire connecting the other side of the capacitor to the battery with no junctions or anything else in between. And so this satisfies those conditions. One wire connecting, and one wire connecting. So where, the orientation of the elements doesn't matter as long as the basic conditions are met. And so you're not changing the diagram by maybe adding a junction. So another way this could work is I could go like that. And if you think about the main idea, that's the same diagram because the positive side of the battery is connected to the resistor. There's one wire connecting the other side of the resistor to one side of the capacitor, and one wire connecting the other side of the capacitor to the negative side of the battery. Same as in this or in this. All of these would represent that diagram. And so what this means is when you have a complicated diagram that may have a lot of angles or bends or whatever in it, try and simplify it, make it the simplest looking diagram you can by taking out angles or taking out long stretches of wire or something like that that really aren't necessary, or bends in wire that aren't needed. So recognize that what's important is how the elements are connected via the wires.